All attendees are in listen-only mode.
Good day. Welcome to SGIA's Basic Color Theory webinar. My name is Ray Weiss. I'm in the Tech Services Department at SGIA, and I'll be conducting this webinar today. The goal of the webinar is to give you a good overview of color and how we interact with it. This is primarily for the color neophyte and is a basic prerequisite for the Color Management Bootcamp. So let's look at understanding color. What is color? These are some of the topics we'll be talking about, the principles. What is color? Color perception, terminology of color, and why can't you see it my way? So we look first at light in the visual spectrum. Thanks to Sir Isaac Newton, we know that white light contains all the colors of the rainbow. He discovered that with his prism-shaped piece of glass. And this will be a very, I would say, crucial point to note. Color depends on three things, three essential elements. One is a light source. What we see here is a sun, an object, in this case an apple, and then an observer. And so we're seeing the head of a person. Let's look at a little bit about how we see. So in the back of the eye is the retina, and contained in the retina are rods and cones. So the rods are about 120 million of them. They are not color sensitive. What they distinguish is between light and dark, and they really come into play with our periphery. Whereas the cones, 6 to 7 million of them, have receptors for red, green, and blue light. The optic nerves transmit electrical impulses to the brain. Vision is a brain function. Our eyes don't send the actual image to the brain. They send that electrical impulse, and then the brain takes that information and constructs what it sees. Color does not exist in the object. Objects either reflect or absorb wavelengths of light. And then if we look here, we see, or we're talking about the human visual spectrum. The typical human eye sees or perceives colors in the 380 to 720 nanometer range of the electromagnetic spectrum. And the eye has peak sensitivities in the red, green, and blue range, obviously going back to those cones that we talked about earlier. So there's many schools of thought on how many colors the human eye can see or distinguish. I'm going to stick with the tried and true number of 10 million. I've seen numbers as low as 1 million, some in the 7 million range. I have even seen, I think it's trichromacity or tetrachromacity, very rare, where people can see up to 100 million colors. Let's use 10 million for the moment. That should suffice for what we're talking about. RGB monitors can theoretically reproduce 16.8 million colors. And we come to that by looking at the three values: red, which is values 0 to 255, green 0 to 255, and blue 0 to 255. If you do the math, that comes up to 16,777,216. For our cases, we're just going to round it up to 16.8 million. And then your typical CMYK printing device can reproduce anywhere from 25,000 to perhaps 75,000 discrete colors. And this depends on calibration, dot structure, halftone used. But the important point is that's less than 1% of all the color that we can see. So let's look a little bit on chromatic infusion. Many of you may know the answer to this question. Is square A the same color as square B? But take a minute just to look at it and think about it. Really, the concept here, I'm hoping, helps dispel the notion that you can visually determine if a color is correct or not. Believe it or not, square A and B are the same color. And I'm hoping this will help to show it more. These bars are the same color throughout. and if you look at them next to A or next to B, you'll see that they match. Probably the next image is going to be a better representation, so we'll move on to that. If you look at these trapezoidal figures, you see two of them. One surrounded by, we'll use the blue of the sky, and then the bottom is surrounded by the dark brown of the earth. The grays appear to be different, but let's do a little experiment. This gray is the exact same as the top gray. We know that because we just sampled the image. And if we impose it on the two, superimpose it on the two, now I hope you can see that it really is the same gray throughout. The difference is the context of the color. So here we have color appearance. And again, we're talking about how the context affects the color. Think about that dress that was the big internet phenom back a little while ago. This was done in 2015, so you'll know when that was. But the green square in the middle is the same. It just appears different because of the larger squares that surround it. So how do we describe color? You'll hear visual terms like light and dark, strong and weak, red and blue. Emotional terms, it's warm, it's cool, it's exciting or soothing. Color mixing terms, it's strong, it's weak, it's dirty, it's clean. Industry specific, pasty, deep, fuller, thinner. But do any of them really tell you, help you reproduce that purple? If you couldn't see it, and I was trying to describe this color for you and saying, well, it's a purple and it looks very royal, it's rich, how are you going to reproduce it? We need some way to talk about that color that we all agree on. And so I would say that establishing a common or agreed upon method of describing color is essential if we're going to share and communicate color. Color tolerance is another important thing for us to have defined. How close must the color match be? I mean, we know from the earlier slide that we can see millions of colors, but our device can only produce, tens of thousands of colors. So we know we're not going to be able to hit every color. So how close do they need to be so that everybody will sign off and say, yes, that's okay? So your customer gives you the approval, and so that you can be confident that you're reproducing the correct color. You need to have some sort of method that you can measure and define what the color should be and what the difference is, or the tolerance. And customer education is going to be number one here. I think we'll take a look at a video that might help show some of the issues involved with trying to describe color without having a defined upon method. So we'll come back in a minute after you've watched the video. So as you saw from the video, having an agreed upon method for defining color and understanding tolerance is very helpful. So now we're going to move on from it. When light wave strikes an object, as you see here, the object's surface absorbs some of the spectrum's energy, while other parts of the spectrum are reflected back from the object onto the observer. The modified light that is reflected from the object has an entirely new composition of wavelengths. Different surfaces containing various pigments. In the case of this image, a bus painted yellow. That pigment of that paint absorbs all the color except for yellow and reflects only yellow. And then we have the light source themselves, emissive, such as artificial lighting or a computer monitor, also have their own unique wavelength composition. So it's just important for us to note. And again, we have the light source, the observer, or the object and the observer. That's what's really an important point to take. And then let's look at some of the pitfalls of visual tolerancing. And by that I mean, if you just look at an image or a group of images and try to use your eyes to spot the off or wrong color, you're going to have a tough time of it. The gray colors in this example on the left, top left, and even the sheep are pretty obvious. because they're so monochromatic, you can see the differences in the color. But if you look at the images on the right, the full color images, they're off the same amounts as the images on the left, but you can't visually see it. And that's one of the reasons why you'll notice the grays are easy to see, and if the grays are right, if the grays are correct, typically the rest of your colors are going to be correct, which is a big driving force behind the G7 movement. The whole point of G7 is to get your gray balancing correct so that you can be confident when a customer gives you an image, no matter what kind of proof or however they try to convey to you what that should look like, if your printer is hitting gray correctly, if it's gray balanced, you can print that image with confidence knowing that it will print out as it should according to the original source. So let's talk a little bit about L star, A star, B star, or lab, as I'm sure many of you, if you've heard about it, that's how you've heard about it. And I'm going to use lab just so you don't have to hear me go L star, A star, B star every minute. The lab color space was created in 1976. The goal was to have a system that defined a color that was not tied to a device. So lab is a device-independent color space. The L is for lightness, white to black, or light to dark. The A is the red and green axis. So if it's got plus A, it's more red, minus A, it's more green. The B is the yellow and blue axis. Again, plus B is more yellow, minus B is more blue. And this creates a three-dimensional color space that defines a color, in this case the color that you see, the L55, A82, B26, is a red. And this color space has been widely adopted and can be used as an objective, system-independent, instrument-based method of measuring and defining color. This is for those of you who just can't wait to see lots of math. When you use a device, in this case we're talking about a spectrophotometer, to measure color, it's important to know how far off or away from the actual color you are trying to reproduce. This is known as delta E, or as my friend Mike Ruff points out, think of the D as deviation, and then you can think of it as the deviation from your intended target. So delta E would be the deviation from my target. CIE, which is the Committee on Illumination, was the first color difference formula, or CIE 76, sorry, was the first color difference formula created when the lab color space was created back in 1976. The goal of these formulas that you see, and this one is the delta E 2000, is to give a value that you can assign a tolerance, an acceptable difference from the reference color. This tolerance, and if you think of it as a sphere around the color, and I'll show you an example in the next slide, is the three-dimensional space. And the size of the sphere, the three-dimensional space and size of the sphere is usually defined as a delta E number. The higher the number, the greater the difference from the reference color. The formula you see above, this one here, was created in 2000 and was designed to bring the formula as close to what the human eye sees. And let's look at the sphere because I think it'll help it make a little more sense. So you see our specified color in the middle of the sphere, and just for the purpose of the slide I'm using a sphere, but these formulas typically will skew the sphere to be more of an elliptical or oval so that it more matches up with what you see with your eye, because different colors, your eye sees different colors different ways, and so the formula is trying to match up as close as it can so that when you say, I have a delta E of 2, so that other color inside of the sphere, we're going to say that's an acceptable tolerance. But when we see a delta E of 9, we're going to say that's not. And in fact, a delta E of 9, it's almost certain that you would see the difference visually with your eye. You wouldn't even need a device to measure it. You would know that you were off. So let's talk a little bit about additive versus subtractive models. We have RGB, red, green, blue, which we've been talking about a lot. And when you add all three of those colors together, you end up with white. Whereas the subtractive colors, CMY, and actually CMYK for all of us in the digital printing arena, or even, in the printing arena, digital printing arena, is a subtractive method. As you add the three, you end up with black. Except we know in the world of inkjet, there's impurities in the inks, so that when you mix cyan, magenta, and yellow together, you're probably going to have more of a muddy brown and not a black, which is why you have the fourth color, K, or black ink. So this is just an interesting slide to look at real quick. It's if you'll notice where the additive primaries overlap, CMY are created. So where red and green overlap, you have yellow. Where the green and blue overlap, you have cyan. And where the red and blue overlap, you have magenta. So the RGB color space is used by lots of different things. Our eyes, for one, right? If we recall, 6 to 7 million cones. They have peak sensitivities in the red, green, and blue range, so that's how our eyes take in color. Cameras, scanners, monitors display color using RGB, but our devices print CMYK. So we need to understand that, and the other thing we know, if we recall from the earlier slide, is our devices are going to print, less than 1% of all the colors that we can see or produce. So we need to understand how we're going to deal with that difference. And let's look at the next slide. I think it'll help a little bit, where we talk about gamut. And gamut refers to the range of color that a device can capture, right? That's your RGB. And if you look at the one on the right, that's the larger of the outlines. That's showing you all the different colors that an RGB device can capture. The outline in the center, the image in the center, is the gamut of the device. So let's just say it's a digital printer. You'll see that it cannot reproduce all the colors that you can see or you can capture with your scanner or your camera, or that you're displaying on your monitor. And so you need to understand that's just important for you to understand that there is a difference, that the gamut, though you can do some work to expand it, it has limitations. I remember I used to teach a class on color, and I would get this question over and over again. Yeah, but so how do I hit this red that I'm trying to hit? Come on, tell me the secret. There must be a secret. Well, if the red's way up in the, if you look at the image on the right of these two, and it's way up in the right-hand corner of the RGB space, the larger of the space, you can see the CMYK device can closely reproduce it, but cannot hit it. And that's not a bad thing. It's not a good thing. It's just reality. So let's talk a little bit about how perception of color varies. So you've printed out this poster, this girl holding a ball with her, or probably a softball, yellow hat, blue shirt. But is it a blue shirt? Is it purple? Is it blue? Is it dark blue? You'll see how it looks different under different light sources. And this is where you can get into real trouble with a customer if you don't understand. So you're in your shop, you've got your fluorescent lights, they approve the print, they go out to display it outside on their signboard, and it looks completely different, and they come back and they want to reject the job. It's why it's important to understand standard illuminance. Standard illuminant is a profile or spectrum of visible light, and it's been published, and we'll look at what I think it's ISO 3664-2009, and it's published by this International Commission on Illumination, CIE, and it's just, actually let's look at a couple of these standards. It'll make more sense. So if we look at the first one, D50, you may have heard this before, that stands for 5,000 Kelvin, or daylight. It's designed to equal approximately sunlight at noon. And this is, there we see the standard, the ISO 3664-2000. That's where that started off at. And we need standards because we all see color differently. Here's another one, D65. Again, these are just different standards, and what matters is that you and your customer agree on a standard that you will both use to view and approve a particular job. Here's some of the different color temperatures. You see how the D5000 or D50 is about there in the middle. 6500 is a little bluer. You get down to 1000 Kelvin in your candlelight. It's really orangish red. So what are the illuminants your clients are using? Are they taking it outside like we just talked about? Are they taking it to a fluorescent countertop? Is it an incandescent environment? Agreed upon illuminants for signing off on the final product is crucial. We say safe practice here, but honestly it's crucial. So let's look at some of those viewing standards. This is the current viewing standard 3664-2009. It's just a technical document focused on lighting design companies. It's not a step-by-step how-to document. There are 5 conditions, and let's go take a look at those. So we have color quality, chromaticity, color temperature. We have number 2, the light intensity. Number 3 is evenness. So it's the evenness of that light that's being shown on the object that you will then observe. The surround is the surrounding of the light booth or the light wall. Does it affect the color? So it's important that that's defined and it's done the way that the standard requires it. And then geometry. And this is the angle at which the observer will see the light reflecting off the image so that there's no glare, or you minimize the glare. And what you're trying to avoid in all this is metamerism. And metamerism is when you have a object, or a, in this case, this card. This card helps to demonstrate it. And so you look at it under agreed upon 5000 Kelvin light, and the blues all look the same. And then you go take it, and in this case, I don't know, it looks like probably a fluorescent or a flash from the camera, and you'll see a little bit of a differential between the blues. And that's because those colors are being affected by the light source, and the observer sees it and sees different colors. So it's important to understand this. So either, you could have a light booth or a light wall, just some place that you and the customer agree, this is where we are going to view and approve our jobs. It just will help you to keep from reprinting a job because, again, of an issue with metamerism that you have no control over. And the last thing to talk about is other factors that affect color are men and women differences. They see color differently. Men are more likely to be colorblind than women. Fatigue. If you're tired when you're going to check out a proof, that can affect the way you see it. You first see it first thing in the morning versus the end of the day. Caffeine can affect it. Your health. Vision correction. We talked earlier about being colorblind. The time of day and mood. Those all affect the way you see color. So I thank you for taking the time to go through this webinar. Again, my name is Ray Weiss. I'm in the Tech Services Department. And my thought is I hope you've come away with a little better understanding of color. If you have questions, if this has piqued you to want to know more, you have a question, please email sgia@sgia.org and reference basic color theory in the subject line. They'll forward it along to me, and I can respond to it. So again, I thank you for taking the time. This ends our webinar.